Maybe not.
Hello, everybody. Can everybody hear me? Okay. Mic's on. Mic is not on. How about now? No. How about now?
Yes, whatever you're doing.
Hello.
Somebody should know how to turn the music on.
Hello.
There we go.
Hello and welcome to inaugural meeting of ACM SIGAI Bay Area chapter. This is the group that three of us had an idea for a few months ago, 6 months ago. Very good friend Steve Alejandro, myself, and Tuna Ozer, we were thinking that there's so much AI research and AI work that happens in the Bay Area, and there's really no place for AI researchers and engineers to come together and discuss the latest developments in the field and create a community that can help and support each other going forward. So we thought that let's put together this group and see how it's going. And today we have a first inaugural meeting. I have no idea how many people are going to show up. Thank you for coming. We have run out of signups, and I think people keep filing in. And next time we'll get a bigger room. Before we get started, I really would like to thank Edmodo for opening up a space for us. Vipul Mittal, who is senior scientist at Google, works and VP of research here, was very instrumental in helping us to get this meeting set up. Ganesh Ramesh, he's also a senior scientist at LinkedIn and now at Edmodo, helped to put this meeting together. I would like to mention Tuna Ozer, as I already said, he's right there. He's a treasurer of the ACM SIGAI Bay Area chapter. I myself is a vice chair. Steve is a chair of the chapter. I also would like to acknowledge Jan Yannick, who's been very helpful to many startups and many groups and any computer science and engineering efforts that are happening in the Bay Area. So thank you, Jan, for videotaping the meeting for us today. You know, we would like to run this group a little bit different from kind of a meetup where we get together once in a while and then go in. You know, we will have regular meetings every couple of months where we invite distinguished speakers to tell us about the cutting edge research that they're working on and hopefully giving the overview of the field and letting us know what are the problems that we can all work on, either from research perspective, from the corporate perspective, startups, or even from an open source development. If there's any open source software that is missing that can really help the community, AI community, to move forward. But we also would like to keep in touch in the meantime and figure out what the needs of the community are. And if people, for example, are starting a startup that is really technically oriented and in the AI field, between all of us here, we have a lot of connections with VCs. We can mentor, we can help to introduce people to investors, and really help engineers to learn about business and startups, as long as they're working on something that is AI related. So it's really focused on the AI area. You know, I'm sure there may be some young researchers that are looking to get into graduate school. We can connect you with professors that can give some advice and mentoring. What does it take to get into Stanford CS department? What does it take to get into MIT, Carnegie Mellon, Berkeley, University of Washington? We would like to also find high school students that are interested in AI and learning about AI, and maybe all of us can help mentor them in their projects. You know, for example, in the Intel science competitions, and reach out to the local, high school community. So we really want to run this group with a goal function, and the goal function is do things that are advancing the field from research perspective, from business perspective, and from an open source perspective. So with that, I will give microphone to Bill MacCartney, who is consulting professor at Stanford and has been teaching natural language understanding for the last 4 years. PhD student at Chris Manning's NLP group at Stanford, senior scientist at Google Research, and one of the smartest people I know. So, Bill, please, it's all yours.
Okay, thank you. Thank you, George. Okay, I want to start with the observation that the nature of personal computing is changing. More and more, personal computing is not about the computer on your desk, it's about the computer in your pocket, the computer in your car, in your TV, on your wrist, on your face. So more and more, we need to talk to our computers, and more we need them to understand the meaning of our words. So my goal today is to give you a high-level survey of the field of natural language understanding, or NLU, and to try to give you a sense of why it's such an exciting area to be working in. Okay, if you're a nerd like me, and come on, you're at a SIGAI meeting, so obviously you're a nerd like me. If you're a nerd like me, you very likely grew up being inspired by stories of robots who could talk. In fact, a big part of the reason I got interested in artificial intelligence is because of stories about robots who could talk. So for decades, we've been dreaming about building machines that can talk to us, that can listen to us, that can understand us. So this is the vision of natural language understanding, computers that can turn words into meaning. In reality, most people's experience of natural language understanding looks a bit more like this, right? And it's a big letdown because you're like, I was promised a lightsaber and a flying car and a talking robot, and I don't have any of those things. Now, it's not really quite this bad. The state of the art is well beyond this now, but we still encounter systems like this. Sorry?
Not at the phone company.
Yeah, we still encounter systems like this all the time, right? And it's very frustrating. One of the most compelling visions of computers using human language was presented in the movie 2001: A Space Odyssey, which came out almost 50 years ago. If you've ever managed to sit through the entire movie, you know that it depicts a future of fantastic technological progress. In particular, the spaceship's computer, HAL, could do all kinds of things that seemed pretty far out in 1967. He had advanced graphics capabilities, he could play chess as well as a human, and he could have a conversation in natural language. So my colleague Andrew McCallum raised the question, how accurate was the computer in predicting what computers would be capable of in 2001? So let's start with graphics. The HAL 9000 had graphics capabilities that must have looked pretty awesome in 1967. It could use different colors, and it could draw circles, and even ellipses, and as a gaming platform, wow. Now, of course, this wildly underestimated progress in computer graphics. Already in 1993, we were able to produce photorealistic 3D renderings of some really scary dinosaurs. Okay, what about chess? In the early days of computing, chess was thought to be a rather stringent test of intelligence. I mean, after all, most humans are really bad at it, and the ones who are good at it are definitely super smart. Nevertheless, HAL was depicted as playing at or above human level. In any case, he could easily beat the astronaut Frank Boole. Now here, the prediction was closer to the mark. In 1997, IBM's Deep Blue finally defeated world champion Garry Kasparov. And I love this photo. I'm not sure if Kasparov has already lost here, but it ain't looking good. Okay, what about natural language understanding? HAL was capable not merely of rudimentary understanding, like what's the weather tomorrow, but he could have these very sophisticated dialogues. So I know that you and Frank were planning to disconnect me, and I'm afraid that's something I cannot allow to happen. It's pretty impressive. So how did this prediction fare? Well, this time the prediction was wildly over-optimistic, almost laughably so. So today we have Siri. And here's Stephen Colbert making fun of Siri when it first came out. He says, I don't want to search for anything, I want to write the show. And Siri says, searching the web for search for anything, I want to write the shuffle. A little bit later, Colbert says, for the love of God, the cameras are on, give me something. And Siri says, what kind of place are you looking for? Camera stores or churches? So I don't actually mean to make fun of a competitor's product, even though it's fun. But getting this right is really, really hard. Although, notice, the problem is not with the speech recognition. The speech recognition is actually pretty good. There's one little mistake, the shuffle, but in general, Siri has no difficulty, or little difficulty, in getting from sounds to words. The hard part is in getting from words to meaning, to intention, to understanding. So that brings me to a point of terminology. You might think, based on the name, that natural language understanding would include speech recognition. But historically, the fields have been quite separate, and the term NLU has been restricted to the understanding of written language. So what does the term NLU refer to? It's a pretty fuzzy concept, but broadly it involves going from words to some kind of representation of meaning. So here are a bunch of topics that involve computers and natural language. I think most people would say that NLP, natural language processing, includes these topics. And NLU is a subset of NLP, a large subset of NLP, containing topics particularly focused on semantics and meaning. But the boundaries are quite fuzzy and open to debate, and even when they're agreed upon, they're somewhat arbitrary. It's a matter of convention and a reflection of history. Okay, here's a roadmap for the rest of the talk. We already did the introduction. Next, I'm going to say a few words about the history of NLU and the impact that NLU is making today. And then we'll take a closer look at 4 subtopics of NLU: relation extraction, semantic parsing, vector space models of meaning, and sentiment analysis. Okay, here's the history of NLU in a nutshell. In the early days of computing, NLU was front and center. Precise, robust understanding of human knowledge was seen as a central goal of artificial intelligence. And there was quite a bit of optimism that it would soon be achieved. People built rule-based systems that encoded lots of linguistic knowledge. And there were some rather impressive successes, but the systems were generally narrow and rather brittle. In the 1990s came the so-called statistical revolution in NLP, which brought some powerful new tools, but also a general retreat from the higher level goals of NLU. The focus shifted instead to lower level tasks like part-of-speech tagging, syntactic parsing, and things like that. In the last few years, there's been a tremendous resurgence of interest in NLU, this time leveraging machine learning techniques and vastly greater computational resources. One of the most important early NLU systems was the Sherdlu system, developed by Terry Winograd, who's now a CS professor at Stanford. Sherdlu is grounded in a blocks world, and it parses the user's input and maps it to a logical form, and then it interprets that logical form in its world and tries to take appropriate action. So here's a sample dialogue, and I think it's pretty impressive. You've got lots of linguistic phenomena. You've got anaphora and ellipsis. You've got complex semantic composition. You've even got pragmatics. For example, this last response reflects the Gricean maxim of quantity. Don't just say yes, be informative. At the time, people were totally wowed by this. I think even 40 years later, this still elicits a wow that this is possible. And this system really had people thinking that human-level NLU was just around the corner. But that optimism crumbled over the following years when later systems tried to deal with more realistic applications. Another early example is Chat80. This is a system developed by Fernando Pereira, who's now research director at Google. This was basically a natural language interface to a database of facts about geography. So things like capitals, sizes of countries, rivers, which rivers flow through which countries, and so on. What's impressive is that it's doing precise semantic understanding and can even handle very complex compositional queries, like Which country bordering the Mediterranean borders a country that is bordered by a country whose population exceeds the population of India? And wow, it actually gets the right answer. I mean, I'm impressed. But it's a very limited domain. You can only ask about geography. And it's very brittle. So you often find that if you ask a question one way, like what countries border Denmark, you get the right answer. West Germany, remember it's 1980, so we still have West Germany. And if you formulate the same question a slightly different way, what countries is Denmark adjacent to, it just says, I don't understand. Okay, fast forward to today. As I mentioned, the last few years have seen an explosion of interest in NLU, both in academia and in industry. Some of the most visible applications today are voice-driven assistants, like Siri, Google Now, and Microsoft Cortana. Also question answering systems like IBM's Watson. But there are also lots of less visible applications, such as legal discovery, which basically means automatically sifting through millions of emails and other corporate documents looking for something incriminating. As you might imagine, natural language understanding is becoming a big focus at Google. One reason is that more and more search activity is shifting to mobile devices, and more queries are spoken rather than typed. And it turns out that when people talk to their phones, they're much more likely to use natural language than when they're typing into a search box. So Google has started making a big push on what we describe as conversational search. And a big part of making that work is understanding the context of the conversation. So instead of a bunch of isolated queries, you have a coherent conversation and you can refer back to earlier topics. There's a really cool video on YouTube that illustrates this, and you should definitely check it out. But here are some excerpts from it. So you can ask about the population of Chicago, and then you can say, who's the mayor? And Google knows that you're talking about the mayor of Chicago. And then you can say, how old is he? Who is he married to? And Google knows who you're talking about. Or you can ask about the San Diego Zoo, and then you can say, is it open? How far is it? Call them. Of course, it doesn't always work perfectly. Getting this stuff right is remarkably hard, but more and more, it actually works. I don't have too much to say about IBM's Watson, but it was a tour de force for natural language understanding, and it generated a lot of excitement about work in this area. Another big application for NLU is in finance, in automated trading. And this is a topic of great interest to me because in an earlier chapter of my career, I was a quant at D.E. Shaw, which is a hedge fund in New York, and I still do some advisory work in this area. These days, almost every hedge fund and proprietary trading desk relies, at least in part, on automated analysis of unstructured data feeds. That basically means natural language text to drive their trading strategies. It turns out you can make enormous trading profits if you can discover and act on market-making news just a little bit faster than your rivals. So things like Microsoft appointing a new CEO, or Russia seizing the Crimea. Essentially, they're using NLU to predict the markets. Actually, it's when things go wrong that the use of NLU in automated trading becomes most apparent. There was a spectacular example of this in 2008 involving United Airlines stock. So the Florida Sun-Sentinel accidentally republished a 6-year-old newspaper story about United going bankrupt. Automated trading systems began to react within seconds, and within 12 minutes, more than $1 billion in stock market value had evaporated. And then, it came back pretty soon. There was an even bigger example last year. You may remember this. The Syrian Electronic Army hacked the AP Twitter feed to report explosions at the White House and Obama injured. The Dow immediately plunged more than 140 points and then recovered within 6 minutes. Look at that. Because this affected the entire market and not just a single stock, it had a much bigger impact. The S&P 500 temporarily lost $136 billion in market capitalization. And this was, again, very likely driven by automated trading systems. So here's a quote from some dude. He says, "That goes to show you how algorithms read headlines and create these automatic orders. You don't even have time to react as a human being." So there are tremendous economic incentives to improve the accuracy and reliability of these NLU systems, and banks and hedge funds are making big investments in this area. Okay, I've been kind of hopping around a little bit, but it's time to buckle down and get organized. NLU is a big field. One way to carve it up is by looking at the kinds of output representation we're trying to produce. So we take a sample of text as input, and we're trying to map it into some kind of semantic representation as output. I'm going to spend the rest of the time looking at 4 NLU tasks which use 4 different representations of meaning. So the first 2 use discrete representations, either relational triples or arbitrary logical forms, and the last 2 use continuous representations of meaning, either scalars or vectors, or sometimes even matrices or tensors. By the way, I'm going to be covering these topics at a very high level. If you're interested in making a deeper dive, a good place to start is on the website for the class that I teach at Stanford, which you can easily find online. Okay, let's begin with relation extraction. So what is relation extraction? Well, let's take a look at an example. What we'd like to do is to take a piece of free text like this, and this is unstructured data, and we'd like to extract a set of relational triples. So with 2 entities joined by a relation. This is structured data. Typically, you begin with a named entity recognition system, an NER system, which identifies the entities and their types. And then the job of relation extraction is to decide for each pair of entities whether a relation holds between the 2 entities, and if so, what relation type it is. So what is this good for? Well, there are lots of applications, but here's one that's become a very big focus within Google. You've probably heard of Google's knowledge graph, which is a huge knowledge base containing hundreds of millions of entities and billions of relationships between them. The knowledge graph is used to power many different Google products and services, so keeping it accurate and up to date is a big strategic priority for Google. But curation is an ongoing challenge because the world keeps changing. New movies keep coming out, companies keep getting acquired, people keep dying. To solve this problem, Google relies heavily, although not exclusively, on relation extraction from the web. Okay, we know what we want to do. Now, how do we do it? Broadly speaking, there are 5 different approaches you might take. The first 2, handle patterns and bootstrapping methods, were prevalent in the 80s and 90s, so I'm not going to spend any time on them. The third one, supervised methods, was the dominant paradigm about 10 years ago. So the basic idea is you manually annotate relation instances in a corpus of text. And then you use that as training data for a supervised classifier that can learn to identify new relation instances. The problem with that is manual annotation is very expensive and time-consuming. So you only get a very limited quantity of training data, and usually only for a handful of pre-specified relations. So the next 2 methods aim to work around that data bottleneck. Unsupervised methods are a very active area of research, but today I'm going to focus instead on an approach known as distant supervision. So here the idea is use the relation instances that you already know about, perhaps because they're already in the knowledge graph, to learn how the relation is expressed in text on the web. And then apply that to discover new relation instances in text on the web. So let me walk you through how this works. The key is to construct a very large training data set without needing any manual annotation by leveraging the relation instances we already have in the knowledge graph. So in the knowledge graph, we've got the founder relation, and we'd like to learn how that relation is expressed in natural language text. We know that one instance is the pair of entities Bill Gates and Microsoft. So we go and find web documents where those 2 entities co-occur. Of course, this requires that we've already done entity detection and resolution on web documents, and that we've indexed them accordingly. Fortunately, that part is already done. Google recently released a data set containing 450 million web pages annotated with free-base entities. So that's available for your use. So here's a sentence where that pair co-occurs. So we guess, although we're not sure, that that sentence expresses the founder relation. So we extract a pattern connecting those two entities and some other features from this sentence, and we construct a training example. Now, here's another sentence where the same pair of entities, Bill Gates and Microsoft, co-occur. This time, they're joined by a slightly different pattern. So we do the same thing. We extract the pattern that connects them and some other features, and we add them to our training example. So each training example corresponds to one relation instance, and it contains patterns and features from all the sentences in our corpus where those two entities have co-occurred. Okay, let's move on to another instance of the same relation, Larry Page and Google. Here's a sentence where those two entities co-occur, this time in a new pattern, so we construct a new training example for that. And we do the same thing for other relations as well. So here's the college attended relation and a relation instance. We find co-occurrences on the web, and we construct a training example. Okay, once we have a set of training data, we can toss it into our favorite classifier, let's say multi-class logistic regression, and train a model which can predict for a new pair of entities what relation, if any, holds between them. By scaling this process up, we can construct a data set that contains billions of examples covering tens of thousands of different relations. And this is far, far larger than you could ever get in the supervised learning paradigm with manual annotation. And massive quantities of training data translates directly into better model performance. So the resulting model is pretty effective. For example, you can learn that Ontario contains Fort Erie, and the band Mighty Wagon is from Cincinnati, and Fyodor Kamensky died in Clearwater, which is a shame. Okay, now let's turn to semantic parsing. Semantic parsing is the focus of my work at Google, so it's a topic that I'm particularly passionate about. The task of semantic parsing is to take a flat string of words like this and map it into some kind of structured, machine-readable representation of meaning, like this, which downstream components can easily turn into action. Now, the details of the meaning representation can vary quite a bit. Here, it's a simple tree-structured object that represents the parameters of the request, with Grand Central represented by a free-base entity ID. But for different applications, we might have quite different meaning representations. For example, one application for semantic parsing is to provide natural language interfaces to databases. In this application, you might want to map natural language questions into SQL queries against some existing database. And note that this is very similar to the Chat80 application that we looked at earlier with the geography questions. Another application that's gotten a lot of attention in recent years is robot control. So here the task is to map natural language commands into some kind of domain-specific robot control language. And an application that's becoming really important at Google is semantic query parsing. That's because a growing proportion of the query stream is not well served by traditional keyword-based information retrieval, especially on mobile. More and more queries are seeking answers which are not found on any web page. So for example, directions to SF by train. It depends where you start, right? Or queries which demand action rather than information. So like, text my wife, I'm on my way. Just imagine what kind of experience the user will have if you simply return web pages containing these query terms, right? Not satisfactory. So in semantic query parsing, we need to define machine-readable meaning representations which vary by use case, and I've shown some examples here. A huge challenge for semantic parsing, just as for other NLP tasks like paraphrase detection or machine translation, is the almost mind-boggling variability of linguistic expression. There are just a million different ways to say the same thing. Far more ways than you would ever imagine until you really begin to mine the query logs. Some people use complete sentences like this. Other people are incredibly telegraphic, like bike GCT. Some people will use explicit trigger words like directions or navigation. Others will say the same thing using only common stop words like how do I get to or take me to. Some will be incredibly precise about the destination, Grand Central Terminal. Others will be super vague, like the train station. Another challenge is internationalization. At Google, the majority of our users are outside the United States. So it's not enough to work only in English. We need to work in every major language. Another challenge is linguistic ambiguity. So when you see a query like Italian reservation in Palo Alto, somebody wants to make a dinner reservation, you might think, okay, we can capture that with a pattern like dollar cuisine reservation in dollar location. And here I'm assuming that dollar cuisine and dollar location are pattern matchers that we've defined somewhere else. Okay? The problem is that pattern could also match this query, Indian reservation in Montana, which could mean that a cowboy has a powerful hankering for some vindaloo, but there's another interpretation which is probably more likely. Similarly, the query mission bike directions suggests a pattern like dollar location, dollar transportation mode, directions. But that pattern also matches the query mission bicycle directions, which could mean the very same thing. But it turns out there's a bike shop called Mission Bicycle, and it's quite likely that the user is looking for directions to the bike shop. So those are two different interpretations. There's been a ton of research on semantic parsing recently, and many different approaches have been explored. But many of the recent approaches have some key elements in common. A context-free grammar with semantic attachments, a log linear scoring model learned from training data, the use of annotators for things like people, locations, dates, times, and so on, and inducing grammars from training data in order to quickly scale into new domains and new languages. So let's start with the grammar. Typically the grammar will have two parts, a syntactic part and a semantic part. And the syntactic part is often a fairly conventional context-free grammar. So we have terminals like Google and non-terminals like $lock. We might have a designated start symbol like $root. And we might also have a special mechanism for indicating optional elements on the right-hand side of the rule, like this. This particular grammar fragment could be used to parse route me to Google in New York by bike, or route to New York by car, or a handful of other queries. So here's an example of a parse for route me to Google in New York by bike. I think most of you guys have seen context-free grammars before, so I won't dwell on this. Okay, now what about the semantic part of the grammar? Every rule in the grammar can come with a semantic attachment, which I indicate here with square brackets and in green. The semantic attachment defines how to construct the semantic representation for the left-hand side of the rule from the semantic representations of the things on the right-hand side of the rule. So for example, in this last rule here, the semantic attachment has this whole expression, get directions, destination $2, mode $3. This is a recipe for constructing the semantic representation for $root. The $2 refers back to the second non-terminal, the $3 refers back to the third non-terminal. So this refers to the semantic yield of $lock. This refers to the semantic yield of $mode. The notation is not that important. Different approaches use different notation. What's more important is the idea of building up the semantic representation following the syntactic structure. So here's a picture of that. This is our example parse again, but this time I've added in green the semantic yield associated with each node in the parse tree. We construct the semantic interpretation bottom up, guided by the semantic attachments for each grammar rule we use. And you may have seen this kind of syntax-driven semantic composition before. If you've taken a compiler's class, there's a very similar idea that you see there, which is sometimes known as rule-to-rule translation. Now, I mentioned earlier that ambiguity is a pervasive problem, and I gave the example of mission bicycle directions. So here I show two different parses for this query and the semantic yield for each. So in this one, we're going to the mission by bike, and in this one, we're going to the bike shop, mission bicycle. So if our grammar supports both interpretations, how do we know which one to choose? The answer is with a scoring function. Here again, there are a lot of possible choices, a lot of possible approaches, but a common choice is to use a log linear model to score alternative derivations. So we define a feature representation which captures key characteristics of the input x, the semantic yield y, and the derivation z. Derivation basically means parse tree. The specific feature representation can vary quite a bit, but it might include things like a Boolean that indicates the co-occurrence of 2 in the input and destination in the semantics. Presumably that's a positive signal that you've got the right parse. Or the occurrence of specific CFG rules or categories in the derivation, or a confidence score from an annotator. This enables us to compute scores for each derivation. So the score for a derivation will be the dot product of the feature vector and a weight vector, theta, which is learned from training data, and I'll come back to that in a moment. And then this is where the log linear comes into it. We can turn that score into a probability by applying the exponential function and then doing normalization. So this is pretty standard, a standard formulation for a log linear model. Okay, what about that weight vector theta? We can estimate model parameters using a variant of the well-known EM algorithm, and you can read more about this in this paper here. So the training data will typically consist of pairs of inputs x and target semantics y, but the training data usually won't contain the correct parse trees z. So we treat that as a hidden variable, and then the learning algorithm alternates between an E step in which we use the current parameters theta to generate an n-best list of derivations for each training example, and an M step in which we update the parameters theta to put probability mass on the correct derivations in the n-best list. And by correct derivations, I just mean those derivations that yield the target semantics. The updates are typically SGD updates, and a common choice is to use the Adagrad algorithm, which was developed by John Ducci. Like I said, there's room for variation here, but that's an outline of a typical approach to this problem. There's been a spate of papers in this area over the last few years, and more than half of them use at least several of these elements, although there's a lot of variation. Okay, now I want to switch gears and talk about vector space semantics. Yes?
I was wondering if you were going to also talk about, so you have multiple meanings for something, why not just ask the user if you meant mission bicycle or if you wanted to get to the mission?
Because we really don't want to annoy the user, is basically the answer. So we want Google to be able to make the right prediction, and the same kind of thinking is at work in search. For example, we usually try to make the right interpretation about what the user is looking for the first time, because users get really annoyed if you're asking them for help. They're like, wait, you're supposed to be working for me, not the other way around. Right? So we try to build the smartest models that we can that make the best interpretation that we can come up with for what we think they need. And oftentimes, it's not that hard. Oftentimes, when you apply the scoring function, it's clear which one is better if you've got the right feature representation. Okay, in the work we've looked at so far, the output of semantic interpretation has been some kind of discrete object. So a relation instance, a database query, or something like that. But in recent years, a lot of the most exciting work in NLU has focused instead on continuous representations of meaning. For example, we might represent the meaning of a word as a point in some kind of vector space. In this example, I show a 2D space, and I've got some points in the space, which are like sciencey words. Now, I've labeled the dimensions here only as D1 and D2. And I haven't said explicitly what they mean. And that's typical of vector space models of meaning. The semantic dimensions are not predefined. Instead, they come out of the model implicitly. But looking at the words, you might guess that this dimension is sort of more about biology stuff, and this dimension is more about physics stuff. One of the useful things about vector space models of meaning is that you can define semantic relatedness between words in terms of some kind of measure of proximity, like cosine similarity or Euclidean distance or something like that. Also, I've shown individual words, but you can easily embed larger pieces of text in the same space. Phrases, sentences, even complete documents. You can put them into the same vector space. And by the way, there's another interpretation of vector space semantics. With appropriate normalization, you can see these points in space as representing distributions, probability distributions over topics. And then you can use probabilistic similarity metrics like KL divergence. Vector space models of meaning have a long history, and they can broadly be divided into two families. In what can only be described as a terminological fiasco, one family is known as distributional models, and the other family is known as distributed models. I did not invent these names. In distributional models, the vector for a word is based on the distribution of contexts in which it occurs. The contexts in question might be complete documents, or they might be just a window of a few words wide around the target word, or they might be specific grammatical relations. So this family includes the well-known TF-IDF representation. It also includes topic models like LSA and LDA. In distributed models, on the other hand, the vectors are typically the output of some kind of neural network model. And this family of models has really proliferated over the last few years with the huge resurgence of interest in neural networks. And we'll take a closer look at a couple of examples of those in a moment. Okay, LDA is a kind of topic model. It's one of the more recent members of the distributional family of vector space models. And it's been very influential. But in the interest of time, I think I'm going to skip talking about the details. Instead, I want to focus on recent work in distributed models, and in particular on neural word embeddings. Word embeddings is just a term of art, which means the set of vectors that come out of one of these distributed models, the points in space for all the words in some vocabulary. These models typically use vector spaces that typically range from as little as 10 dimensions to maybe as much as 1,000 dimensions. Here we're looking at a word embedding in a 100-dimensional space that was produced by Joseph Turian in 2010. Of course, you can't easily see 100 dimensions, so he used a visualization tool called tsne to project the 100-dimensional space down to 2 dimensions. But the words are still too small to be legible, so let me zoom in on this. If you zoom in, you see that, indeed, words which are semantically or syntactically similar tend to get clustered nearby in this space. So here we've got a bunch of countries. Prime is in there. Not everything is perfect, but here's a bunch of words that have to do with leaders, I guess. There's a bunch of finance stuff, days of the week, and some time adjectives. These are some light verbs, and some verbs that are related to saying stuff. So that's pretty neat, and it's very useful. This can be an input to a lot of different NLP tasks that we're interested in. But what I'm going to show you next is even more remarkable. In some of the most recent embedding models, we find that not only are similar words nearby in the embedding space, but directions in the embedding space can encode the type of similarity. This is hard to see in a 2D projection like you get from tsne. But in a 100D space, there are a lot of different ways to be nearby. So, for example, if you focus on the points in the embedding space that represent countries, you might find that the capitals tend to be a certain distance to the right. And you might find that the languages for each country tend to be a certain distance below. And the currencies tend to be a certain distance behind. In a 100-dimensional space, you've got a lot of different directions to work with. Those directions can capture a lot of information. One model that has this property is the so-called word-to-vec model, which was introduced by Tomasz Mikolov and others at Google last year. This is a form of skipgram model, which is a very simple neural architecture in which the goal is to learn word vectors that best predict nearby words. So the objective function is just the conditional log likelihood of the words in a fixed window around the target word. And because this model is so simple, it's highly efficient and scalable. And in fact, by using a couple of additional clever tricks, they were able to train an embedding model with 1,000 dimensions on 33 billion words in a single day. And this is both much higher dimensionality and a much bigger training corpus than any previous embedding model. And the authors were able to demonstrate that the result was a much better model. And by the way, you can download it. It's available on Google Code. Question?
So in the case that you have word sensitive ambiguity, for instance, Paris is the name of a person and the name of the city, how does that, do you see representation of Paris, or do you see the point moving in the proper direction to represent both person and the city?
That's an excellent question. Most of these models don't attempt to do any word disambiguation before applying the model. And so when you have ambiguous words, you often wind up getting very messy mixtures where you have the point floating somewhere in space that's not really near neighbors of either sense. Oftentimes, however, there's one sense that dominates. So, for example, with Paris, it is both a city and a name. My guess is, in a large corpus, the city sense strongly dominates the name sense. And in that situation, you're going to find it clustered with the other cities, not with the name. But there are some words where it's very evenly split between two or even more different senses, and then the results aren't so satisfying. Yeah?
Another question. Who decides the number of dimensionality? The system itself, or the person, or is it fixed?
It's fixed. It's a parameter to the system. People who do these experiments will often experiment with different numbers of dimensions. The number of dimensions strongly affects both how long it takes to train the model. More dimensions means it takes a lot longer to train, but it also means that you very often get better results on whatever task you're trying to apply this to. And I'll show you a task in just a moment where we try to use this model. One of the ways that they evaluate the usefulness of a model like this is by examining its ability to capture specific kinds of semantic relations between words. So here you see a projection of this 1,000-dimensional space down to 2 dimensions, and you see a bunch of countries and a bunch of capitals. And the amazing thing is, there seems to be a particular direction in this space that represents the relation between countries and capitals. And this fact enables some really neat vector arithmetic. For example, if you look at the vector between Spain and Madrid, and then you translate that vector so that it originates at Japan, well, it winds up right here. And if you look around nearby that point, hey, there's Tokyo. Now, it's not perfect, right? It's not exactly where Tokyo is, but it's pretty close. And very commonly, the closest thing to that point is Tokyo. So I think that's pretty amazing. Another way to look at this is if you take the meaning of Madrid, meaning in the sense of the vector in this space, if you take the meaning of Madrid and you subtract out the Spanishness, and then you add back in some Japaneseness, what you get is Tokyo. And the first time I saw this, this just blew my mind. I think that's totally astonishing. And it's not just for capitals. This works for lots of kinds of relations. By the way, nobody programmed this into the model. They weren't aiming for this. This isn't part of what they were training the model to achieve. All they were training the model to achieve was, this is the objective function. The objective function is predict nearby words. Do a good job of predicting which other words are going to show up nearby. That's it. That's all the model is aiming at. So it works not just for capitals, it works for lots of kinds of relationships. And in order to evaluate this model, they constructed a test set containing 3,200 analogy problems. So these are just like the analogy problems that you may remember from taking the SAT in high school, unless you're very young, because they stopped doing this, they stopped putting it on the test in 2005. But if you're older than 27 or so, you probably remember this, and if you went to high school in America, you probably remember this from the SAT test. So just like the analogy problems on the SAT, the task is to predict the fourth item from the first three. So if you're going to do that with a vector space model, the way to do that is to take the vector for New York Times, subtract the vector for New York, add the vector for San Jose, find the point where you wind up, look around, and see what's nearby, see what the nearest vector is, the nearest point. And if you get San Jose Mercury News, hey, you got the problem right. So that's essentially the challenge. The word-to-vec model that I described achieved 72% accuracy on this task, which, by the way, is way higher than the average high school student. They also found something else cool. You could do similar kinds of vector arithmetic with words that explicitly name the relationship involved. So for example, if you take the vector for check and you add the vector for currency, and then you look at the four nearest neighbors, this is what you get. And I mean, 3 out of those 4 are sort of, kind of, maybe correct. The first one is definitely correct. The last one is an abbreviation for that currency. Czech crown, I guess that's a misspelling, but it seems sort of like the right meaning. And then this is a currency for a country that's next to it. Zloty. Okay, so another misspelling. Okay. There's a lot of messy text on the web. This is built from text on the web, and you know, people don't really know how to spell that well. So it's not perfect, but it's pretty good. You know, if you look at some of the other results, I don't know who Cécile D is, but I think the first 3 are all French actresses. Something a little weird happened here. I don't know how Upriver got in there, but like overall, I think you'd have to say this is pretty impressive and pretty amazing that this actually works. The obvious question is, but why? How does this actually work? And I'm not sure that I can give a completely convincing explanation. I'm still trying to wrap my own head around this. But it has to do with the fact that the embedding implicitly represents the distribution of contexts in which the word occurs. And to be a little bit more precise about that, because of how the training objective is formulated, the embedding represents the log of a probability distribution over contexts. So the sum of 2 vectors represents the product of 2 probability distributions. And product here corresponds to conjunction. So check plus currency represents the product of the probability distributions of the context for check and for currency. And which word is common in both of those contexts? Karuna. So that's the closest that I can come to an explanation of how this actually works, why this actually works. And once you get that, this also explains how this stuff works. Okay, our last topic is sentiment analysis. Sentiment analysis is an area that's been really hot over the last few years, especially with the rise of social media and Web 2.0. Of course, you've got product reviews on Amazon, you've got restaurant reviews on Yelp, movie reviews on Rotten Tomatoes, and there's growing interest in using Twitter to predict economic and political sentiment. The traditional approach to sentiment analysis is pretty simplistic. You define a lexicon of positive and negative sentiment words, and then you just count them up, right? You take the positives, the number of positives minus the number of negatives, and that's some kind of measure of your sentiment. So if a review says, best movie of the year, a triumph, you've got 2 really positive words there, so that's a great review, that's a 5-star review. If the review says slick and entertaining despite a weak script, you do have a negative word, but there's 2 positive words, so that's still a pretty good review. If the review says an abysmal failure, you've got 2 really negative words, so that's a 0-star review. Okay, but a big problem with this approach is understanding how semantic composition affects sentiment. It's one thing to count up positive and negative words, but it's really hard to account for the role of context. So, for example, negation. You might think that negation simply inverts the sign of a sentiment word. But it's actually more complicated than that. If somebody says a movie is not an abysmal failure, sorry, that is not a very positive review. That's maybe a 1-star review, not a 5-star review. Another example is the X but Y construction. So if somebody says the movie was fun, sweet, and earnest, but ultimately unsatisfying, you've got 3 positive words and 1 negative word. But really, this is kind of a negative review. This is maybe a 2-star review, right? In this X but Y construction, it's the Y that dominates the sentiment. And you kind of just have to know that about the X but Y construction, that that's how sentiment works in this construction. So my colleagues in the NLP group at Stanford have developed a model called the recursive neural tensor network, which can learn how sentiment works in these constructions and in many others. The idea is to parse the sentence using a standard syntactic parser, and then to associate a vector representation with every node in the tree. So again, our semantic representation is a vector. And these vectors can be mapped onto sentiment labels, which are shown here. Blue is positive, red is negative. So we start at the leaves, and we've got a bunch of positive words down here. Cleverness, kind, intelligent, humor, for some reason, is especially positive. I'm not really sure why. But the real magic happens when we start doing semantic composition. So the vector for each internal node is computed from the vectors of its children, using a particular kind of tensor product that I'll describe more in a moment. And the parameters of the tensor are learned from training data. So here's the crucial bit. This whole subtree here, cleverness, wit, or any other kind of intelligent humor, that whole subtree has positive sentiment. But then when you put it inside this negation, doesn't care about, that inverts the sentiment. And the model needs to be able to predict that. So the tensor encodes knowledge about how sentiment works in this construction and many other constructions, and we wind up correctly predicting that the overall sentence is a negative sentence, even though pretty much every single word in this sentence is either neutral or positive. The simplistic approach would totally fail here because there's so many positive words. So how do you train a model like this? Where does the data come from? Here's what the Stanford team did. They took 10,000 sentences from movie reviews. They parsed them with the Stanford parser, which is a probabilistic syntactic parser. That gave them 215,000 phrases corresponding to constituents in the parse tree, so basically subtrees within the parse tree. They then asked raters on Mechanical Turk to assign sentiment labels to every single one of those phrases, and multiple raters for each phrase. So this enabled them to put sentiment labels on every node in every parse tree. And if you go, the data is publicly available. If you go to the site, you'll see graphical depictions of all the trees. I just copied and pasted just the first row here. But you can actually see what they all look like, and it's kind of neat to see. So here's a little bit more detail about how this model works. The semantics of words and phrases are represented by 30-dimensional vectors. As I mentioned, composition happens via tensor product, and this diagram indicates how it works for the simplified case of 2-dimensional vectors. So they're actually 30-dimensional vectors, but that's a little hard to capture. If they were only 2-dimensional vectors, it would look like this. So in this case, the tensor, which is this orange or red thing here, has dimension 4 by 4 by 2. If you don't know what a tensor is, it's, so you have scalars, which are 0-dimensional. The representation of it is 0-dimensional. You have a vector, which is like an array with 1 dimension. A matrix is like an array with 2 dimensions. A tensor is just an array with 3 dimensions, right? So this tensor, in this case, is going to have dimension 4 by 4 by 2. Each of these dashed boxes represents one slice through the tensor. And so this is one slice through the tensor, and this is another slice through the tensor. And each slice can capture a type of influence that a child can have on its parent. So to compute this tensor product, we take the two child vectors, the left child and the right child, each represented by a vector of length 2 in this example. We concatenate them together, and then we multiply them on both the left and the right by this matrix. Then we add this other thing that I'm not going to explain. Then we take the result and we pass the result of that through this function f, which is a sigmoid function, which is a very standard thing in neural networks. We train this thing using backpropagation through the network structure. Again, this is very standard in neural networks. And the training objective is to minimize the KL divergence between the predicted distribution of sentiment labels and the distribution that we got from the Mechanical Turk raters in the Stanford Sentiment Tree Bank. And this model is able to achieve 85% accuracy on sentence level sentiment, which is pretty impressive. And there's an online demo, so you can go and play with this yourself. In this demo, you can type in your own sentence, or you can find your favorite movie review and paste in a movie review, or a sentence from a movie review, and see what sentiment it predicts for it. It's a lot of fun. Yes, question?
How about sarcasm?
Sarcasm is a really difficult problem. You may have seen that a few weeks ago, maybe a month ago, there was something from the CIA or DARPA or somebody in the government is sponsoring research on sarcasm and how to detect sarcasm. And actually in the news coverage of that I read, they quoted this guy, Richard Socher, who's just finished his Ph.D. At Stanford. And he was so bold as to venture some guesses as to how you might apply very similar methods to detecting sarcasm. I myself am a little bit skeptical that it's that easy to do. Like many things in NLP, I think getting the easy cases, the obvious cases of sarcasm is probably quite straightforward, but really capturing sarcasm in its full richness, I think is going to be very difficult to do. Yes, question?
So the plus or minus, is that based on a 3-star threshold?
For this figure of 85% accuracy, I don't know whether they binarize the results or whether they're looking at the full distribution. Certainly for the training objective, they're not simply looking at a binary distinction. They're actually trying to match the distribution.
Yeah.
But I'm not sure on what basis this figure is computed.
The reason I bring that up is because there's noise in the response that they're getting. So,
Definitely.
A plus minus could be a penalty on just something that it's capturing.
Yep, that's true. Question?
Yeah, you mentioned about sarcasm. What about some terms that we commonly have that are, like the movie was really bad, or the movie was a bomb. I mean, that's not sarcasm. That's a commentary, but it means different things. That movie was really bad could mean a good thing. So how do you deal with that?
So you're talking about words that are actually ambiguous. The meaning of the word is ambiguous, right? A bomb could be. Are you talking about the fact that bomb could be used in a kind of slangy way to like it was the bomb, like it was really good?
Same
or,
thing with bad.
Yeah.
The movie's really bad. That's slang.
Yeah.
Right?
Yeah.
But it also could mean it's a really bad movie.
Yeah. Again, I think that's really hard to capture. It kind of depends whether it's represented in your data, in the data that you train the model from. So, it's typical in modern NLP that the best models that we have are trained based on statistical analysis of very large data sets. If the phenomena that you want to predict is there in the data, there's a decent chance that if you've got the right feature representation and the right model type, you'll be able to uncover it. So if it's actually there in the data that bomb is commonly being used in a positive sense, you have a hope of being able to recover it. Now, if it's very mixed, if it's often used in a positive sense and often used in a negative sense, then in order to distinguish those, you're going to need some kind of features, some information that's put into your model that enables you to distinguish those contexts. you can imagine that that might be possible. There might be other words that are used in the review that might bias you towards a slangy interpretation rather than a straight interpretation. But if that second sense is not even in your data, your model's not going to be able to learn it. It will only be able to learn it if it's there in the data. Yes?
So I mentioned the first was trained on more formal English.
That's right.
While sentiment analysis on movie reviews is going to be more informal.
That's right.
So I imagine there's some issues parsing there, but also I imagine in movie reviews they're going to use emoticons. Well, emoticons don't probably exist.
That's often true. I'm not sure how true that is in this data set, but it's very true on Twitter. And Twitter is a big focus for sentiment. And actually, when people do sentiment analysis on Twitter, they need to be very careful about the way they tokenize the text. Because if you use an off-the-shelf tokenizer, if you use like an open source NLP package, and you just use the default tokenizer, typically it will see the emoticon as just, it doesn't know about emoticons basically, so it sees it as some punctuation, and by default it will split that punctuation up, and you'll lose the meaning of the emoticon. There exist tokenizers that are specific to this application that know about things like emoticons and will keep the emoticon together as a token. And then if you do that, you can actually very easily learn that like a smiley face is positive sentiment and a frowny face is negative sentiment. The other thing you asked about was the domain mismatch between the training data that's used for training the syntactic parser. The syntactic parser that they use in this experiment is what's known as the Stanford parser, which is trained on Wall Street Journal text. It's very clean text that's been edited by a professional editor. And it is somewhat different from the text that you'll find in movie reviews. So that domain mismatch can sometimes create problems. I don't have a good sense of how big a factor that was in this work, because this isn't my work. I can tell you that the same group, Richard Socher and others that he works with, have also used similar techniques to try to learn parsers from scratch. And that given appropriate data, they could potentially try to use these same techniques to learn a parsing model that would be more appropriate for the domain. Did you have a question?
Yeah, I was wondering, in something like Twitter or mailing lists or something like that, you've got a couple of problems, one of which is you've got a community which may evolve a certain vocabulary or a certain way of talking about things, and you also have words that show up dynamically a lot. Topics will show up and then will get cut down to a shorter form and things like that. It seems like would be a real challenge.
It definitely can be. I think I would come back to the same answer that I gave before, which is that it all depends on what data you train on. And this is it's a pervasive problem. It's certainly a problem that we need to be conscious of at Google. We need to be constantly updating the models that we use to reflect how the world is today. So, for example, before 2009, if you typed iPad into Google search engine, it would try to spell correct you to iPod because we didn't know about iPads. And if we hadn't updated our models, then you would still find in 2010 and 2011 and 2012 that when you typed in iPad, we're correcting you to iPod. We need to recognize when the iPad comes into the world, we need to realize that we need to discover that the iPad exists, that language has changed, actually. Language is constantly changing. And so we need to be continually updating our models, and that means continually finding new data and retraining our models accordingly. So there's language change, there's specific communities of language use that you refer to, and these all create complications for this very data-driven approach. Yes?
That brings up another question. Do you actually version the parsers and apply the 2010 parser to text that's tagged as 2010?
Interesting question. I mean, a lot of the work that I've been talking about here is academic work. I don't think that's typical in academic work.
I'm thinking of Google.
At Google, we don't really keep around models from 5 years ago. So
Google incorrectly parsed older text.
I suppose, I mean, I think it's not a big source of errors. I don't think language has changed that much in the 15 years that Google's been around. Yeah. Sorry, I don't know who was next.
How would you incorporate context that may, so because this leaves out everything outside of the actual text itself, other information that you could input to,
When you say context, are you thinking about other sentences in the same document?
Data that might improve the parsing. For example, the gentleman at the back mentioned some slang. If you could mention that this text belongs to some subculture, then that could help improve the.
I see. That kind of information could potentially be injected into the model, but again, because it's a model that's been trained from data, you would need to find a way to have that kind of information in the training data as well. So you would need to find a way to encode information about the context into the training data, and if you did that, you would have a good chance of recovering that in the training that you do of the model. But it might be a challenge to figure out how to encode that information and how to collect the appropriate kind of training data. Yes?
I mean, you could have, just like they do with speech recognition, before they used to increase the vocabulary, they would personalize the training. You could have like somebody's personalized engrams. You could, and you wouldn't necessarily store it for everybody, but it's like, how do you bias that person's engrams with a few coefficients to modify a generic one? And you could use like cookies to store that, or like.
Yeah, that's absolutely right. So this is something that is done in speech recognition at Google and at Microsoft, and I assume other places that do speech recognition as well. There's increasingly personalization of the language models that are used to recognize your speech. Oftentimes it's not at the individual level, although that's a possibility if we have individual information about, for example, who's in your address book. If we know the names that are in your address book, that can enable us to do a better job of recognizing those names when you say, call Vivek or something. We can do a better job of recognizing that name if we know that name is in your address book. But sometimes it's at a slightly higher level. There can be geographical customization of the language models that are used in speech recognition. So if we know that you're in New York, we might know that, I don't know, in New York there's Houston Street, right? So maybe we'll do a better job of recognizing Houston Street because we know where you are. I'm not familiar with people doing similar kinds of things for sentiment or for semantic parsing that I mentioned earlier, but it seems like the same ideas could be transferred over.
No, like if Vimeo, the Atlantic Monthly, they did a visualization of like that Harvard dialect study.
Uh-huh.
It was really interesting, and they describe things without, and they try to see which word they're going to choose, and that would be generic, like northeast, southeast.
Right.
But then also for like a propensity to use sarcasm would be something where it might be very valuable, or like if they're on a Google groups, like this vocabulary is more likely in this Google group because they're talking about it.
Yep.
Yeah. But for an individual, it would be like this person it's more probable for them to use sarcasm.
Right. Yeah, I think it's all a question of having the right data to put into your models, because you don't want to be trying to hand engineer this stuff into your models. That just doesn't scale. It's not something that you can do at massive scale for hundreds of different languages, for hundreds of millions of people. In order to do this at scale, you need to be automatically learning this stuff from data. And so if you want to be able to capture these kinds of complexities in your model, you need to find a way to have that complexity represented in the data that you train your model from. Yes?
You mentioned retraining the model when the data changes.
Mm-hmm.
How hard is it to retrain these models or add additional training data into them?
Retraining is not that hard conceptually. It's basically a question of running a command line. There's a big question mark about how much computational resources it takes. For this specific model, I don't know, although I have a bibliography and you can go read this paper and it'll say in the paper how long it took. There's quite a bit of variation in how long these models take to train. I mentioned the word-to-vec model, which took only a day to train on a single machine. I think this one took considerably longer than that. On the other hand, I'm pretty sure it didn't take a year to train. The other question you raised was about, I think what you meant was incremental training.
Yes.
So basically having a model and without needing to retrain the entire model, add in additional data to move the model from where it is today. For these neural network models, the kind of training, the kind of learning that's done is online learning, which means that incremental training is relatively straightforward. And that's quite different from, for example, like some of you may be familiar with SVM classifiers, which is a different kind of classifier with a very different style of training, which is not online. And doing incremental training of SVMs is not straightforward. Maybe there's been some research on how to do that, but I'm not familiar with it. It's by no means straightforward. With this, it's very straightforward. You just sort of do some more iterations of the same training, and it's easy to toss in additional training data. Yes?
So I'm going to ask a slightly complementary question. Lack of data is fine, because what you see is in some sense what you can learn, right?
Mm-hmm.
But with a place like Google, you have the complementary problem where you have too much data. You have a lot of data, plenty of data, right? And then sometimes the context gets hidden with a lot of noise that surrounds the data, right? How do you deal with it in terms of disambiguating, clearing all that stuff so that you get to know what are the end context that makes sense?
That's a tough question. I might be able to give you a partial answer to that. I don't know if I can give you a completely satisfactory answer. One of the, so I've been talking about these neural models, these neural network models, and this fits into a theme that's been really big over the last couple of years. You may have heard the term deep learning, and this is sort of part of that general trend in computing. One of the most interesting applications for deep learning is something called unsupervised feature learning. And an example of that is in image recognition. Or image classification. The image classification task is basically you're given an array of pixels, maybe it's a 64 by 64 array of pixels, and you need to identify what's in the picture. Is it a boat? Is it a cat? Is it a coffee mug? This is a super, super hard problem. Older approaches to this problem would rely on manually specified features. So there will be, people would write little feature functions that basically look for edges in the image and look for corners in the image and then look for conjunctions of edges and corners and so on. But all those feature functions would be manually engineered. And one of the big breakthroughs that deep learning has brought to this problem is making it possible for a very deep neural network that has hundreds of thousands of nodes in the neural network and maybe 10 layers in the neural network to automatically discover those features without them needing to be manually engineered. If you step up a level from that specific application, what's going on there is that the neural network is automatically identifying what are the most predictive aspects of that data. So the neural network is automatically pulling out from the data the best sources of signal. We're in the very early stages of this research right now, and there's been a lot of progress made in this specific task of image recognition, lots of progress as well in automatic speech recognition. People are starting to get excellent results in natural language processing, but I think a more comprehensive to your answer to your question is still in the future. We don't yet have a fully general answer to how to detect noise, or to pull signal out of noise in every application. Yes?
What kind of challenges have you seen adopting these kind of neural network models to different languages, or is it pretty much agnostic?
The model itself is pretty much agnostic, so it's a question of whether you've got the right data. If you've got the data, that's actually part of the beauty of this approach. It's one of the main arguments for this approach. For example, I'll take machine translation as an example. In the old days, people thought that the way to do machine translation was to have an army of linguists who would write down this very complex sort of rule-based model of how each language worked. That general approach didn't get really far. People started on this approach in the 50s, and by the 80s and even the early 90s, they really hadn't gotten very far with this approach. And part of the problem is that it requires sort of manually engineering this knowledge into the model. Starting in the early 90s, people started using a much more data-driven approach to machine translation. And actually, this work was pioneered at IBM Research in Fred Jelinek's research group. And there's a famous quote from Fred Jelinek. Supposedly, I don't know if it's true, supposedly he said, "Every time I fire a linguist, my scores go up," meaning the scores on his translation model. Because the approach that they pioneered was this very data-driven approach where instead of trying to manually engineer all this linguistic knowledge into the model, all you do is learn at massive scale from a parallel corpus of data, which words correspond to each other. And you compile a model which just consists of a whole bunch of statistics about word co-occurrences. So, sorry. I think the answer is, if you've got the data, you can use a statistical model to learn a good model. The data doesn't exist for every language. There are some languages that are low resource languages, and that's a problem. Yes?
So actually, in relation to this question, this model that you showed in the context-free grammars
Yep.
presentation, and some of the other tasks, like, for example, entity extraction, historically, kind of hard to scale to new languages. I mean, with COG, I would imagine you have to construct grammar. Have you guys done anything to generalize and extrapolate faster from, let's say, English or a few languages to new languages? Have you found ways to do this more efficiently, other than just go and cater to the grammar or cater to the features with extraction, let's say?
The answer is a little bit different for different tasks. For example, take the relation extraction task that I talked about. The approach that I described, a distance supervision approach, actually translates across languages pretty well, provided that you have some seed instances with the right names in the target language. Because the whole idea of the distance supervision approach is that you use those seed instances to learn automatically how the relation is expressed in the target language. And that's very transferable across many different languages. But it does depend on having the names. You need to know how you say Microsoft in Chinese. I don't know how they say Microsoft in Chinese. It's probably a little bit different from how we say it. So you need to know that if you want to be able to translate this approach into Chinese. For a task like syntactic parsing, the approaches that are still dominant in syntactic parsing require having lots of manually annotated data in the target language. Stepping up a level, there's one of the trends that we've seen in NLP over the last 10 years is a move from supervised approaches where you require lots of manually annotated data more toward unsupervised approaches where all you need is, so to speak, raw data, like raw text on the web without any manual annotation. Typically, when you make that move, you initially pay a cost in terms of performance. There's a lot of research on unsupervised models for syntactic parsing, but the performance of unsupervised parsers is a lot lower than the performance of supervised syntactic parsers because they're working with less information. They don't have that source of supervision. But the gain is that it makes it possible to sort of break that data bottleneck, the bottleneck of relying on lots of expensively generated manual annotation.
In the case of the unsupervised syntactic parser, is it like a reconstruction error that they're trying to minimize? Is it the same autoencoder type of concept?
Yes, for some of the neural network approaches to syntactic parsing, that's right. Yeah, it's exactly trying to learn a representation which enables you to recover the original structure with minimum error. Yep. Yes.
So I'm wondering, with Twitter data, the data is, first of all, the sentences are barely English. You have an enormous amount of variability, or I should say change, and with hashtags or slang, it's very, very dynamic. What I'm wondering is, have you seen a contrast between, let's say, learning the syntax, where you learn the syntax versus treating them like a bag of words, and then doing, like you said, SVM? Have you seen that there's any kind of real significant lift between doing a syntactic parse?
So if you're referring specifically to the task of sentiment analysis, so I'm not an expert in this area, but my sense is that if you're working with Twitter data, an approach that's based on syntactic parsing is probably not going to yield great results. The syntax of tweets, such as it is, I mean, there is syntax in there, but it's weird, it's different, it's definitely not like the Wall Street Journal. And most of the available syntactic parsers are trained in the Wall Street Journal. So it's probably not going to work that well. Doing sentiment analysis on Twitter is a very active area of research, though, and people have developed lots of techniques and sort of tips and tricks that are specific to the quirks of this particular data source. And if you're interested in knowing more about this, my collaborator, Chris Potts, he's the guy that I teach the class at Stanford with, he's done a lot of work in this area. And if you Google his name, Christopher Potts, you can find on his website, he has a lot of information about doing sentiment analysis on Twitter. So I mentioned earlier the issue of tokenization on Twitter and making sure that your tokenizer knows about smileys, and it also needs to know about hashtags and needs to not split up URLs and lots of other things, very, very sort of practical, nitty-gritty concerns for doing sentiment analysis on Twitter. This is a problem that people have made lots of progress on. Yes?
I'm curious, going way away from Twitter in another direction, has any of this technology been used to do clustering of scientific papers to say, okay, here's some papers I'm interested in, find these others or similar?
Yes, absolutely. In fact, there's been work at Stanford. There was a project called the Mimir project at Stanford, which applied, in particular, some of the topic modeling stuff that I kind of skimmed past. I had one slide on LDA, but I didn't spend any time on it. It's closely related. This particular project was a joint effort between some people in the CS department and some people in the School of Education. And they're very interested in looking at sort of the evolution of scientific fields over time and cross-disciplinary work and how those cross-disciplinary efforts sort of come together and break apart over the span of years. So I think it's been an area that's been really interesting, not only for people in computer science, but for people in social science to look at these trends in intellectual history based on analysis of language. Yes?
Give some examples of NLU in the field of investment management. You were referring to some benchmarks.
Yeah. There's mainly two different areas that people look at in finance and that they're interested in. One is, and they're both areas that we've talked about. So one is relation extraction, and the other is sentiment analysis. So relation extraction, you can imagine that if you're able to do relation extraction with high quality on breaking news, on a news feed, you can learn about potentially market-moving news, instantly. Of course, you might get it wrong. You might think that UAL went bankrupt when it really didn't. But you can see the potential appeal of being able to extract that structured data almost instantaneously from unstructured data. The other area that's been a big application is sentiment analysis. There's been a series of papers over the last few years that have made some bold claims about the ability of sentiment analysis, in particular on Twitter, to predict the markets. There was a paper by Ballin et al. in 2011 where they claimed to be able to predict the Dow with 87% accuracy, like 6 days in advance, using sentiment analysis on Twitter. Don't believe the hype. There were a lot of methodological problems with this study, but not surprisingly, it got a ton of media coverage. People went bananas over this, and they actually, some guys actually started a hedge fund based specifically on this research, and they raised $100 million to invest. 2 years later, they went out of business. But just because that particular experiment was a bad experiment, bad methodology, doesn't mean there's nothing there. And a lot of people think that there might be something there, and that it might be possible to measure the economic pulse of the country or the world by looking at people's use of language on Twitter. So I think it's an interesting area for further research.
I was going to say maybe last question, and then we can take questions individually after from everybody.
Yes.
One last question. So in the case of the word-vec model,
yes.
You have this issue of word sense disambiguation. Is it possible to use context as a latent variable for the words? So maybe you have like one of 10 contexts you can apply, which gives you 10 possibilities for each word. If a word's only used in 2 different contexts, I think most of those points would lump into 2 clusters, but if you really had 10 different uses, you might get 10 different points.
Yeah, so it depends what you mean by context. If you mean the immediate context, like the words surrounding it?
Oh, no.
Okay, because I was going to say that's exactly what the model does.
Oh, no,
actually.
no. I mean, for example, having 10 vectors represent that word and then inferring which of those is most likely to occur. So having a latent variable z represent the context and a vector for that word per each element z.
I see. But those...
Still minimizing reconstruction error.
Yeah, so those, if there were different senses at work, those would only get teased apart if there is something actually in the data that reflects that.
I was thinking of like person running versus a refrigerator running are clearly 2 different senses of the word run.
Yeah, but that will show up in the local context, which is exactly the thing that's being captured by this model. I think I see your point now. In order to make that work, you would need to let the model have multiple vectors per word.
Exactly.
And in the model as it is today, you only have 1 vector per word. That's right.
Yeah, so turning on an engine is more like starting a refrigerator or having it run, which is very different than a human at the starting gate running.
That's right.
Yeah.
Yep. Okay, so I think I'll stop there. This is actually my last slide. I think it's pretty clear that we still have a long way to go before we're going to be able to have a conversation with C3PO. But I hope that I've also convinced you that the field of NLU is moving really fast, and there's a lot of exciting things to look forward to. And I'll stop there. Thanks very much.
Bill, thank you very much for the great presentation, and the part on the vector space semantics just blew my mind. I've never seen that before, and it was very, it was pretty amazing. So we can have the room maybe for another 20-30 minutes. Please, introduce each other to each other and have a conversation. There is still food and drinks in the fridge. And if you haven't signed in when you walk in, please do so. I will send supplemental information for the talk. The location of the Bill's class, NLU class of Stanford, Chris Pollitt's website, and Bill, the slides will be
Yeah, I'll put them on my website.
Yes, and the link to the slides available from Bill's website. Thank you very much. Go ahead.
I have a quick question. So you mentioned that some experts may be willing to advise like startups. So is there a way to identify those? And
I think over the next weeks and months we're going to learn who is in the part of the group, and I will send a general email for everybody to ask questions. So I think I'll create some sort of a Google group, and then you can send the questions. It will come to the organizers, and we will identify people who can help people that need help, technical things or startups or anything else that we could help. And again, the goal here is to create a community that helps advancement of the AI technologies, and that's what we are working to do. Thank you very much for coming, and please get more food and drink, and we'll have more meetings to come. Thank you.